Welcome to this video where we will have a closer look at the random walk model and non-stationary asymptotics. Let us first consider this case where we do not have a drift term in the model. So delta is equal to 0, the constant from before. Then the random walk model without a drift can be compactly written down like this, where the series indifferences delta yt is equal to our IID error. Or alternatively, yt is equal to its previous value plus the error term. Or even more, yt can be expressed as a partial sum of the first t error terms. In our derivations, we will often set this initial condition y naught equal to 0 for just ease of exposition. So in that case, the value of our time series y at time point t is exactly given by the partial sum of our error terms. Now we will also continue to work with error terms that are IID with sigma squared as the variance of this normal distribution. Now, if you think back of one of the questions in the first tutorial week, or the tutorial from last week, we actually looked at the AR1 type of model where the parameter phi is smaller than 1 in absolute value. And we found there that the limiting distribution is a normal distribution with this asymptotic variance. Now, a random walk model looks very similar to an AR type of model equation. The only difference being that, let's say, this AR parameter phi is exactly equal to 1. Now, while that might look like a small difference, it actually has enormous consequences. Because when phi is equal to 1, we say that we have a unit root. And if we look at this expression over here, we would have a normal distribution with mean 0 and variance 0. So we would actually have a distribution that collapses to a point mass at 0. And that is, of course, not useful for hypothesis testing. So the scaling by root t for unit root processes is actually not the appropriate one to give us a desirable limiting distribution. Or in other words, we will need to blow up this difference over here by yet another power of t. So we need another asymptotic rate of convergence or a scaling factor to obtain a non-degenerate asymptotic distribution. And to determine this appropriate scaling and derive the limiting distribution, we need to rely on a very important building block, other important building blocks, such as the scaled partial sum process, XT. Remember that in our unit root model, yt was expressed as the partial sum of the error terms, namely the error terms up until time point t. So it's no surprise that this partial sum will also become very important. So consider here the scaled partial sum process where we look at a fraction r of the sample over which we sum. As of now, I'm going to make use of this notation also over here to round an integer a. Now, for any realization, our scaled partial sum process is a function. You can view it as a function of varying r, as denoted over here by xt dot. So you can view this guy as a random function since r can vary. But of course, for a given r, it's a random variable built up of these IID error terms, the epsilons. Now, how does a realization of our scaled partial sum process look like in practice? Well, here is an example. Let's say that we have 10 observations, so capital T equals to 10. And we can visualize this realization as a function of R displayed on the horizontal axis, where R goes from 0 up until 1. And remember, R is the fraction of the errors over which I sum. So when I draw 10 IID errors, at R is equal to 0, I sum none of them. So the value of my scaled partial sum for R equal to 0 is equal to 0. Now, when R is equal to 1 over T, so when I have a fraction 0.1 in this case, my first error term starts entering. And I'm jumping to this level over here. At R equal to 2 over capital T, or 0.2 in this case, then I have the partial sum of my first two error terms, and I arrive at this level, and so on. So any realization of my scaled partial sum process results in this step function for R, the fraction of the sample over which we sum the errors. And you can write this out like this. Remember, at R equal to 0, we start at 0. Then the first observation enters for R equal to 1 over capital T, and we have its value divided by root T. When the second observation enters at R equal to T over 2, we have the scaled partial sum of the first two observations, all the way then up until the end for R equal to 1, when we have the scaled partial sum over all error terms, T equal to 1 up until capital T. Now, what are the properties of this scaled partial sum process? Well, we've seen that the process starts at 0 for R equal to 0. We also have a step function at multiples 1 over T, capital T. And each of the increments is mutually independent, as they are built up from IID errors. Also, any increment which boils down to a partial sum of IID errors is normally distributed. Now, we assume that our error terms are IID normal, but in generally, actually the scaled partial sum process for fixed R also goes to a normal distribution by a central limit theorem. Now, what do these properties remind you of? Well, you should just have taken a course on stochastic processes, and then these properties should remind you of a Brownian motion. As a refresher, I copied here the definition of a Brownian motion on the slide, where you indeed recognize the property of starting at 0 and the increments being independent and any increment having a normal distribution. So in the derivation of our limiting distributions, these Brownian motions will pop up. And we will make use of yet another device that you have seen in stochastic processes, namely the functional central limit theorem. What does this theorem tell you? Well, the functional central limit theorem tells you that our random function xt scaled by sigma converges in distribution to a standard Brownian motion or a Wiener process. So this guy over here is a random function. The limit should also be a function with increments distributed as a normal. And that is exactly our standard Brownian motion process. So we have here actually a central limit theorem on functional spaces. Now, this statement for our random function should actually be understood as uniform convergence. What do we have written out over here? Well, the largest amount over all R by which our scaled partial sum at fixed R differs from our Brownian motion, well, this difference should converge in probability to 0. Or in other words, if the sequence of random variables converges in probability to 0 when we take the supremum over all values of R, we say that the sequence of random functions over here converges in distribution to our standard Brownian motion. So we've seen our Brownian motion and the functional central limit theory. And these are important devices on which you need to rely for your asymptotic distributions later on in this course. We will need one more ingredient before we can actually look at the derivations. And that is the continuous mapping theorem for functionals. Remember from the previous lectures that the continuous mapping theorem allowed us to nicely combine certain results. Namely, if let's say xt converges in distribution to x, then for any continuous function g of xt also converged in distribution to g of x. Now we need a continuous mapping theorem for so-called functionals. What are functionals? Well, a functional is a function that takes a function as an input, transforms it, and returns something else as output. So let's have a look at these two examples over here. The first functional takes the function f as input and maps it to another function, namely a scalar multiple sigma of it. The second example takes the function f as input. It takes here this integral, and so it maps the function into a scalar. Now our continuous mapping theorem tells us that if we have a sequence of functions st, so that if a sequence of functions st converges in distribution to a stochastic function, and g is a continuous functional, then the convergence in distribution is maintained under this transformation through the continuous functional g. How can we make use of this theorem in our context? Well, remember, we know that this scaled partial sum process converges in distribution to our standard Brownian motion. In the definition here from the previous slide, this guy is our sequence of functions st that converges in distribution to our stochastic function s. So then this theorem tells us that for any continuous function g that is applied to this guy over here, the convergence in distribution is maintained. So let's look at two examples. The first one where we just have xt. And we need to determine the limiting distribution. So what is the functional g in this case? Well, it takes this guy over here as an input, and it multiplies it by sigma. So we know that xt converges in distribution to the same transformation g of our standard Brownian motion. So we also need to multiply this guy over here by sigma to establish this result. Now let's have a look at the second example. That is the square of xt. It again takes this guy over here as an input. It squares it and it multiplies it by a factor sigma squared. to get rid of it actually. So we know that xt squared converges in distribution again to the same transformation G of our standard Brownian motion. So what is the same transformation? We square our Brownian motion and we pre-multiply it by sigma squared. Now you will practice a lot more with these examples yourself in all of the upcoming tutorials, since many examples will pop up in our derivations. Now we have all building blocks in place to use these results in our random walk model without drifts, and the initial condition, we just put that equal to 0. Remember that yt is equal to the partial sum of our error terms. So how do we arrive at our partial sum process? Well, we need to do some rewriting over here and scaling, rescaling by 1 over root t. And then we also have 1 over root t in front of this sum over here. And the upper part of the sum, small t, I'm going to rewrite that in terms of this index R, which is the fraction of the sample over which we sum. Or in other words, small t is equal to R times capital T over here. And then we recognize here already our scaled partial sum process that is popping up. So we will be rewriting our partial sums of the errors in this format, such that we can then make use of the functional central limit theorem or the continuous mapping theorem if we have certain functions of it. So it also won't be hopefully a surprise then that our limiting distributions will contain expressions with Brownian motions. And in the next video, we will dive into these derivations.